Howdy. This will be our first lecture for ELE 210 circuit theory. I've prepared a review document, actually a couple of these documents, so I'm going to go to the first one, and hopefully you're seeing my screen right now. And so our first review packet is we're going to start out with stuff that we've learned in Electronics for Technicians 1 and 2. And we're going to start out with some resistive circuits. And we'll start out at first with the total resistance method, and obviously the way that works, we want to combine groups of series and parallel resistors step by step to get the total resistance. We compute the total current using Ohm's law, and then we solve for the rest of the circuit's voltages and currents, starting from the total current and working through each combination of series and parallel clumps of resistors that you formed in step 1. So I'm going to bring up our first example here, and this is a combination circuit, certainly. As we visually inspect this circuit, we see that we have R1 is in series with a parallel combination of R2 and R3, and that in turn is in series with a parallel combination of R4, R5, and R6. And we can indicate that in a formula, if we will, right here. R total equals R1 plus the parallel combination of R2 and R3 plus the parallel combination of R4, R5, and R6. So given that we know that, we can go ahead and compute the resistance of these clumps that we've made. And why don't we start off with the one that's R4, R5, and R6. Here's our parallel resistance formula in its most general form. And if you remember, when the resistors are equal in parallel, we can just take the resistance value of the individual resistors and divide it by the number of resistors in parallel. So 12 k ohms over 3 gives us 4 k ohms. And this would actually just fall out of this equation. If you put 12 k ohms for R4, 12 k ohms for R5, and 12 k ohms for R6, you'd have 1 over 3 over 12 k ohms. Well, 1 over 3 over 12 k ohms is the same as 12 k ohms over 3, and that gives you 4 k ohms. So we're taking things a little easier here by using some equal value resistors, just so that we don't have to go off in long-winded calculations. But I trust that you folks can do the 1 over 1 over formula here and come up with the right answer. The next clump of resistors was R2 in parallel with R3, and there's a couple ways we can do that. We can use the general formula. We can use the formula as two resistors of the same value, so we can take 8k divided by 2 and get 4k. Or we can use the product over the sum, in which case we're going to get 8k times 8k would be 64k squared ohm squared. Divide it by 16k ohms, and you'll wind up with 4k ohms. So R total is the combination of R1, parallel combination of R2 and R3, and the parallel combination of R4, R5, and R6. In each case, they're 4k, so they add up to 12k. Now, the next step in the total resistance method is to get the total current. So we use Ohm's law. IT equals VT over RT. VT, I will slide up here, obviously that's 24 volts. We've computed RT to be 12k ohms. And so we have 24 volts divided by 12 k ohms. And just to review the engineering notation stuff here, 24 volts is 24 times 10 to the 0. And 10 to the 0 is 1. So they got that many volts, and it's divided by 12 times 10 to the 3, because K means thousands and 10 to the 3 is thousands. So 24 over 12, 10 to the 0 over 10 to the 3. Well, 24 over 12 gives us 2. And then when we divide, we subtract the exponents of 10. So we have 10 to the 0 minus 3, or 10 to the minus 3 here. So I have 2 times 10 to the 3 amperes. And 10 to the 3 is 1,000ths, or milli, and so the answer is 2 milliamperes. So our total current is 2 milliamperes. And now we have enough information to find the remainder of the voltages and currents through the circuit. Since this is a series circuit consisting of multiple single and parallel combinations, we start with the total current. Series, we know, we recall from Electronics for Technicians 1 that in a series circuit, the current is the same through the circuit. There are no highways for the current to enter or leave. So if you think of this circuit as R1 is a glomp, R2 and R3 together is a glomp, and R4, 5, and 6 together is a glomp, whatever current flows out of our 24 volt supply has to flow through R1, it has to flow through the combined glomp of R2 and R3, and it has to flow through the combined glomp of R4, 5, and 6. I don't even know if glomp is a word, Okay. At this point, we know that our total current is 2 milliamps, and it's the same throughout the circuit. So VR1 is going to be the current through R1 times R1. That's Ohm's law. And the current through R1 is the same as the total current. Okay, we have, now that's the line up here. I total is equal to IR1. It's equal to the current through the parallel combination of R2 and R3, and it's equal to the current through the parallel combination of R4, R5, and R6. All those currents are 2 milliamperes. So we start off with R1 and IR1. Again, it's going to be 2 milliamps because it's the total current, times 4K. So 2 times 4 is going to give us 8. The milliamps is minus 3. The K is plus 3. When we multiply, we add the powers of 10. And so we wind up with 8 times 10 to the 0, which is 1 volts, or 8 volts. So there'll be 8 volts across R1. Now, because the parallel combination of R2 and R3 and the parallel combination of R4, R5, and 6 are also 4K, just like R1, we know that the voltage across the parallel combination of R2 and R3 and the voltage across the parallel combination of R4, R5, and R6, those are both going to be 8 volts also, because they have the same current flowing through them, 2 milliamperes. They're all 4K ohms, so they're all going to wind up with 8 volts. So we're going to wind up, as I go back to our diagram here, we're going to have 8 volts across R1, 8 volts across the parallel combination of R2 and R3, and 8 volts across the parallel combination of R4, R5, and R6. And so we start off with a 24 volt rise, so we could call that minus 24. Then we add our voltage drops. We get a plus 8, that takes us to minus 16. Another plus 8, that takes us to minus 8. Another plus 8 takes us to 0. We've finished the loop, and we came up with 0 as a total of the voltage rises and voltage drops around this loop, which satisfies Kirchhoff's voltage law, or KVL. Now that we know, I shouldn't go that far, we know there's 8 volts across, say, this parallel combination of R2 and R3. Well, if there's 8 volts across 8K, there should be 1 milliampere flowing there. And the same thing here, 8 volts across 8K, 1 milliampere flowing there. And so if we just do the Kirchhoff's current law at this node, we have 2 milliamps total current flowing in, and we have 1 milliamp going out and 1 milliamp going out. So our current entering this node and our current leaving this node add up to 0. which is, or they're equal. If you want to assign them signs, they add up to 0. And the same happens at this node. You got a milliamp coming in here, a milliamp coming in here, and 2 milliamps leaving, so we're all balanced. Now, when we come down to this node, what we ought to find is we got 3 equal resistors, so the current should split equally. And if I take 2 milliamps and I break it into thirds, I'll get 2/3 of a milliamp here, 2/3 of a milliamp there, and 2/3 of a milliamp there. Now let's see what our computations came up with. There's our 1 milliamp for the current through R2 and R3. Now the current through R4, R5, and R6, again they're identical, will be the voltage across the parallel combination, 8 volts, divided by 12K. That will give us the voltage, that'll give us the current through one of these resistors. This, by the way, is a little mistake and probably should be R4. Sorry about that. I will make sure the handout is updated so it says R4. And so 8 over 12, well, that is 2/3. And volts over K, well, we can look here. It'll be 8 divided by 12. You know, if you divide the top and bottom by 4, you get 2 on the top, 3 on the bottom. That's 2/3. That's the same as 0.6666 repeating. So we have that number, 0.666. And then we have 10 to the 0 on top, 10 to the 3rd on the bottom. That gives us 10 to the -3. So we have 0.667. That's what this approximately equals here is. I didn't want to have, you know, you can't obviously put in an infinite number of 6's here. So I just put 0.0667, it rounded up. And so I got 2/3 of a milliamp here, just as we thought we would. And if you're being real strict about the scientific notation, this answer is typically acceptable. People don't mind 0.667 milliamps. If you are being strict about engineering notation, you would go to 667 microamps, because this is a number between 1 and 1,000, and then micro is 10 to the -6. So you've got a you've got an exponent that's a multiple of 3. Now we have the voltage across and the current through every resistor in the circuit, albeit we did benefit because I set the problem up with a lot of equal resistors to make things, compute more directly. We're going to see that also in problem 2 here. In problem 2, I've just changed things a little bit. Instead of a series combination of parallel resistors, I've got a parallel combination of series resistors. Just trying to show generality here. And our driving signal in this case is not just a DC voltage, it's a pulse of sorts, which I've graphed down here. So, you've got a 12K resistor in parallel with 2 6Ks that are in series, in parallel with 3 4Ks that are in series. So you can see I'm trying to make things come out nicely. Now this waveform repeats every 400 microseconds, and it's high for the first 100 microseconds and low for the last 300 microseconds. So the period of the signal, since it repeats every 400 microseconds, is 400 microseconds. And the frequency is the reciprocal of the period, so F equals 1 over T equals 1 over 400 microseconds. Here's our scientific notation. And we get 1 times 10 to the 0 over 400 times 10 to the -6 seconds. And we come out with this number, 0.0025 times 10 to the 0 minus a -6. So that's 0.0025 times 10 to the 6. So if I move this decimal point over 1, 2, 3, I make this number bigger by 3 decimal places. I have 2.5, and I take this 10 to the 6th and I shrink it by 3 decimal places, and it becomes 10 to the 3rd, 2.5 times 10 to the 3rd hertz, or 2.5 kilohertz. The duty cycle of the pulse is, when you have these rectangular pulses, you can talk about the high duration as a percentage of the period. So we have 100 microseconds over 400 microseconds. That's a quarter, but we express it as a percentage. So you can multiply that by 100 and you get 25%. So our signal is a dynamic signal instead of a steady DC voltage. But the circuit is purely resistive, and if you remember me harping from electronics for technicians 1 and 2, this circuit is nothing but resistors, and all these things do is they convert electrical energy to heat immediately. There's no delay. So in any current or any voltage we measure in this circuit, we will see the same waveform here. There'll be no delay. It'll be a pulse, that's high for a quarter of the time and low for 3/4 of the time. The only thing that'll change is this amplitude of the pulse. And here it's 180 millivolt pulse. So that's what we start with. But whatever we measure, it's going to look like this because resistors don't have any delaying function. They don't distort the signal. They just convert the electrical energy to heat immediately. And so we have that property going on for us. So we're going to do our total resistance method. So let's apply the total resistance method again. In this case, our total is the parallel combination of R1 with R2 and R3 in series, and with R4 and R5 and R6 in series. So R1 is 12K, and you can see how I've rigged this one, 6K and 6K for R2 and R3, and 4K, 4K, and 4K for R4, R5, and R6. So our total is equal to 12K in parallel with 12K in parallel with 12K, and we use our formula, the general formula, 1 over 12K plus 1 over 12K plus 1 over 12K. Now these all have the same denominator, so you can add them up. That's like 1 over the quantity 3 over 12K. Well, 1 over anything in a fraction, you can just invert the numerator and denominator. We have 12K over 3, which gives us 4K. So we have a total resistance of 4K. To compute our total current, the total voltage is 180 millivolts. We divide that by 4K. So I have 180 times 10 to the minus 3. Remember, milli is thousandths. So 180 times 10 to the minus 3 volts divided by 4K, or 4,000 ohms. So 4 times 10 to the 3. And 180 divided by 4 is 45. And again, we subtract our exponents of 10 when we divide. So I have times 10 to the minus 3 amps, which equals 45 times 10 to the minus 6 amps, or 45 microamps. So our total current waveform is a 25% duty cycle pulse of frequency 2.5 kilohertz, and its amplitude is 45 microamps. Since this is a parallel circuit consisting of multiple single and series combinations, multiple single and series combinations. That is, we have single resistors and series resistors, and they're combined into a parallel circuit. We start with the total voltage, which is the same across every branch of the circuit. So all the parallel branches up here, everybody up here sees 180 millivolt pulse at 2.5 kilohertz with 25% duty cycle from the top to the bottom of R1, from the top of the series combination of R2 and R3 to the bottom of that combination, and from the top of the series combination of R4, R5, and R6 to the bottom of that combination, there is 180 millivolts. Okay. Well, 180 millivolt pulse, but we can just treat it like a DC voltage while we're computing, and then when we give the answer. We just say, remember it's a 25% duty cycle, 2.5 kilohertz pulse train. So we computed the current here. I total equals 45 microamps. And now we're using this voltage. The first resistor, R1, is 12K. So to find IR1, the voltage across R1 is the same as the total voltage. Here's one of those statements again. This is the parallel equivalent to what we set up above when we said the total current was the same as the current in the individual branches. Well, here the total voltage is the same as the voltage across the individual branches. So, in parallel circuits, there's only one voltage. And in series circuits, there's only one current. So we're using that to our advantage, and we're going to say that the current through R1 is equal to VR1 over R1. Well, VR1 is V total, 180 millivolts, and R1 is 12K, and we compute this thing. And once again, now we have 180 over 12, 10 to the minus third over 10 to the third, and so we're going to wind up with microamps again. But we're going to get 15 microamps. So a third of our current, third of the 45 microamps, is going through R1. If I look at the current through the parallel combination of R2 and R3, the series combination of R2 and R3. So I take the voltage across them, which again is the total voltage, is 180 millivolts. R2 plus R3, they are two 6K ohm resistors. They'll add up to 12. I'm going to get the same 15 microamps. And you can see, once again, I've rigged the problem to come out a little easier for demonstration purposes. The current through the series combination of R4, R5, and R6 is the voltage across those three resistors, which is the total voltage, which is 180 millivolts. And you add these up, and you get 4K plus 4K plus 4K, the same 180 millivolts over 12K resistance in that branch gives me 15 microamps. It didn't go out of my way here to add these up, but if I add up R1, if I add up IR1, I of the series combination of R2 and R3, and I of the series combination of R4, R5, and R6, 15 microamps plus 15 microamps plus 15 microamps gives me 45 microamps. We certainly want Kirchhoff's current law to be satisfied. So the current flowing into here is 45 microamps. We're going to lose 15 here. So you could say there's 30 microamps flowing here. We lose another 15 here, and then there's 15 microamps flowing there. And so the 15 microamps, 15 microamps, and 15 microamps all combine again to give us 45 microamps. And so at these two nodes, the top node, which extends from here to there, and to there, Kirchhoff's current law is satisfied because you got 45 microamps coming in, and when you look at all the exits, you got 45 microamps going out. Similarly, in this bottom node, which extends from here, include ground in it if you like, up to here and here and here, it's all one node, you've got 15 microamps entering from three different paths, combining to 45 microamps and returning. So Kirchhoff's current law is holding, and our let's go down here where we calculated everything. So now the voltages across these various resistors, we already know that the voltage across the 12K ohm resistor, R1, VR1, we know that's equal to V total, and it's 180 millivolts. Now, in that series combination, the middle branch where we have R2 and R3 in series, once again, I'll go back up here, R2 and R3 are in series. So this guy has the complete total voltage across them, 180. these are two equal resistors, so it's not surprising that they're going to have 90 millivolts across here and 90 millivolts across there. And here it's not surprising that you're going to have 60 millivolts, 60 millivolts, and 60 millivolts. Because all these guys got to add up to the 180 that's being applied to the circuit. And they do. And without boring you to tears, you can see that the IR equation, V equals IR, works out that way, that the current in each case is 15 microamps. So if you've got a 6K ohm resistor, you wind up with 90 millivolts a pulse amplitude. And the same here. And then if it's a 4K ohm resistor, you wind up with 60 millivolts pulse amplitude 3 different times. So let us go on to problem 3, which is can we simplify a big mess? And all we want to do, we're going to find the total resistance and current of the circuit below. And it's kind of a big mess, but it's not as messy as it could be. So this one is solvable. It's possible to create one of these things with certain loops in them where you'd have to use simultaneous equations and kind of get nasty with that. And we will talk about that this semester. But just as a review, to look at this thing, I'm just going to go down here and attack this thing. And what's the first thing we're going to do? We're going to combine R3 and R4 in series and call it R34, and that's a 2K resistor. We're then going to combine R34 and R5. Wait a minute. Yes. We combine those to be 2K. It looks like I jumped the gun with this picture and combined R1 and R2 that are 1K in parallel and called them 500 ohms. Then I went back here and made them 1K. Again, I'm so sorry for that. We know that R1 and R2 are going to be 500 ohms because it's two 1K ohm resistors in parallel. So that's coming, 500 ohms. Here we do the parallel combination of R34 and R5. And you can kind of do this one in your head. It's the product over the sum for these two resistors right here. 2 times 1 divided by 2 plus 1 is 2 over 3, or 2/3 of a K, which is going to be 667 ohms. So there we go with that. Now we have our 667 ohm resistor here. It's in series with 1K, and we have our two 1Ks in parallel, and you can see what's going to happen to them. The two 1Ks in parallel, like we foreshadowed there, they go back to being 500 ohms. These two that were in series combined together to become 1.667 K ohms. And they're still in parallel with this 1K ohm resistor. And when we do this parallel combination, you could kind of think of this as 3/3 and 5/3. So when you multiply them together, you get 15/3 over 6/3. And what do you get? Actually, you get 15/9 over 15/9 over 5/3, and that gets you to, never mind. That's 3/3, that's 5/3. Multiply them together and you get 15/9. When you add them together, you get 5/3. So 15/9 divided by 5/3 will get you 5/8, I guess, which is 625. So you get 625 ohms in that combination. Now you got 500 in series with it. At last, you combine those and you get 1.125K, 1125 ohms. And simple Ohm's law thing, you divide 12 volts by 1.125K ohms and you get 10.667 milliamps, and that comment is a goof. So that's the answer there. And that is the end of the first review sheet. So again, hopefully you found this posted in course content, and homework with this kind of junk in it will be forthcoming. And I'll try not to make it too onerous because we want to get on to some fun things in this semester. So see you next time. We'll do review packet number 2. Okie doke. Take it easy, and we'll see you again soon. Bye.